In this video, I will explain you Lemma 6.1.1. You can see this lemma in the topic edge covering. Okay, fourth unit of edge covering. So this is the first lemma that you can see under this topic. Okay, so let us start reading the statement. Let G be a connected graph. That is, they are given you a connected graph, that is G, and they are saying that graph G is not an odd cycle. Okay, that is the most important condition. It should be a connected graph first, but it should not be an odd cycle. It means it can be the connected graph with the even cycle. Is that clear? Till this, is that clear? I will show you with a figure. That is, they are talking about the graph G, right? So, and that they are saying that graph G is connected graph, right? And they are saying this graph is not an odd cycle. So I'm choosing this graph. This is the graph. Look at this. Okay. This is a connected graph, right? And this connected graph is having even cycle, right? Because number of edges, this is a cycle first, am I right? Because when I start from this vertex, I can come back to the same vertex again. So this is the cycle. So in this cycle, how many edges you are having? 1, 2, 3, 4. 4 edges you are having. That is even number of edges you are having in this cycle. Right? So that you can say this graph, this G is a connected graph with the even cycle. So from this statement, they are asking us to consider this kind of graph. So we have considered. Now next, if there is a graph like that, then what we have to prove is this G, our graph G has a 2-edge coloring. This graph will have 2-edge coloring. It means I'm going to color this graph with the 2 colors. Is that clear? So we know that when coloring, adjacent edges should not get same colors. That is what the condition when coloring the edges. So here I'm going to color this. I'm coloring this edge with the color 1 and this edge with the color 2, and I can color this edge with the same color 1 because they are not adjacent to each other, right? This edge present here and this is here. They are not sharing common vertices. Okay, the vertex of this edge is these two and the vertex of these edge is these two. There is no common vertex for these two edges, right? So they are not adjacent. So I am coloring the same color 1 with this edge and I am coloring this edge with the 2, right? Because these two are not adjacent. So I have colored this graph with what? How many colors? 2 colors. So G has 2-edge coloring, right? Okay. In which both colors are represented at each vertex of degree at least 2. That is, there are 2 colors. Consider any vertex. If I consider this vertex having colors, before that, the degree of this vertex is what? 2. In our statement, they are saying that the degree of the vertex should have at least 2. Okay, it means you can also have more than 2 also. But compulsorily, you will have 2, you will have a vertices with the 2 degree. Okay. Okay. So here I have a vertex and the degree of this vertex is 2. So that condition I satisfied. And what they are saying is each vertex, okay, having degree 2. So this is one edge and this is another one edge for this vertex. So that 2 edges will have different colors. Okay. Okay, both colors, this is 2-edge coloring, so both colors you are representing for a vertex having degree at least 2. Is that clear? So that is what we have to prove. I explained it using a figure. From the figure, the statement is satisfied, right? So that is what you are proving now. I hope you understand, right? For every vertex, look at this, in which both colors are represented at each vertex. Each vertex, these 2 colors should get represented. Okay, the degree of the vertex should be at least 2. So all the conditions are satisfied in this figure, right? So let us prove it. Okay, let us prove it. So for that, we can follow my notes. Okay, here you can see the proof of this lemma. First, you are assuming G is a non-trivial. It means what? Trivial means a graph will have only one vertex. It should not have, that is, I will tell you, trivial means the graph will have no edges. Okay, the graph will have no edges is called a trivial. So here you are considering non-trivial graph. It means what? A graph that is having so many edges. So that kind of graph you are considering. Now you are going to prove this with the two cases. In case 1, you will say that G is Eulerian, and in case 2 you will say G is not an Eulerian. So here when I say Eulerian and not an Eulerian, you have to know what is Eulerian, right? So I will explain you what is Eulerian. Eulerian means, the definition is, if you want to say a graph is an Eulerian, it should have Euler tour. Okay, when I say this definition, you may raise a question, what is Euler tour? Euler, you have to know, if you want to understand what is Eulerian, you have to know what is meant by Euler tour. Is that clear? I will explain you both. Okay, listen, I am erasing this and I will explain you what is Eulerian. Before that, you have to know what is Euler tour, right? Usually what is meant by tour? Tour means if you start from this point, if this is a bus stand, you are going to a tour. Okay, you will visit so many places, right? And you will come back to the same place. That is what tour, right? So the same thing also here. Look at this. What is Eulerian? A graph which contains Euler tour. Okay, I am drawing a graph now. I am going to say this graph is an Eulerian. Okay, can you see this? Okay, so listen, you are starting your tour from this. This is your bus stand. Imagine you are starting tour from here. I will tell you what is Euler tour. The definition first. Euler tour means it travels every edge. I will show you. Okay, I will show you. If I say, then you might be feeling confused. Look at this. Euler tour means, a Euler tour is a tour that traverses, means that travels each edge exactly once. Okay, every edge should get traveled. The condition is only one time edges should be traveled, and they are not talking about the vertex here, right? It means you can repeat the vertex. Okay, vertex can be repeated, but edges, what? Edges should not be repeated, and also you have to cover all the edges, but there should not be repetition. Is that clear? Look at this. Here I am starting from this vertex. I am going to visit all the places. I told you vertex can be repeated. Okay, vertex can repeat it. Okay, I will travel all the places and I will come back to the place where I have started. So here I am going to tour from this, and I will come to this place, and then I will come here, and then I will come here. Okay, and after that I will come here, and from here I will come back to the same place where I have started. So look at this. I traveled all the edges, right? I traveled this edge, this, and the edges is not repeating. Vertex is repeated. When I cover, already I reach here, but after going here and I will come back to the same vertex. What I told, vertex can be repeated. That's not a problem. So I have completed all the edges, right? And I came back to the same place. So here you can see Euler tour. Euler tour means what? A tour that travel each edge. That is important. Each edge should be traveled, but the condition, only one time you have to travel, right? imagine, even if a tour, if you are going to the, if you are traveling from one place, if you are going back to the same, traveling the same place again and again, that will be boring, right? Yeah, that is why you have to travel each edge but exactly once. Okay, so here you can see Euler tour, so that this graph is called what? Eulerian. Okay, I hope you understand what is Eulerian. Now let us come back to our proof. Okay, so here in our first case, you are saying the graph G is what? Eulerian. It means you know that it contains Euler tour. If there is an Euler tour means what? There will be, surely there will be a cycle, right? Here you can see a cycle. Look at this. If I start from here, right? This is one cycle and this is another one cycle. Okay, if it is an Eulerian, and Eulerian means there will be Euler tour. Euler tour means surely there is what? A cycle, right? So that is what you are writing. Then G contains a cycle. After this line you have to write then G contains a cycle. So here in the statement they are given you that cycle should not be an odd cycle. In the statement they are given you, so that you are saying that this G is an even cycle. In this graph you are having odd cycle. This is the example that I have put to make you understand what is Eulerian. Okay, don't compare this figure with our proof. Okay, this is just for an understanding. Okay, so here in the statement they are given you, you should not have odd cycle. So here clearly our graph G will have what? Even cycle. That is what you are writing. If there is no odd cycle means then surely there should be a cycle. If it is not odd means it will be even, right? So that is what you are saying. Therefore, if it is an even cycle means what? There will be even number of edges, right? That is what you are writing, which can be alternate. If there is an even number of edges, again come back to the same figure here. First I have drawn a figure, right? But from when I read the statement, I have drawn this figure. Okay, look at this figure. If there is even number of edges means you can alternatively assign the color 1 and 2. Here look at this, which can be alternatively assigned the color 1 and 2. It means if I color this edge with 1, then I can color this with the 2, 1, 2. Alternatively you can color. If this is 1, this is 2, 1, 2, right? Yes, if you can color like this, then what is mean by that? G has a proper two-edge coloring, because you are colored with the two colors and the coloring is proper. Proper means what? You are not coloring the same color for the adjacent edges, right? For adjacent edges you are not coloring the same color, so that this coloring is what? Proper, right? Otherwise, in the next page you will see, if you are not able to color the graph with like this, if you are not able to do proper two-edge coloring, then there is another case. That is what you have to do is, otherwise G has a vertex V0. Okay, if you are not able to color the graph in a proper two-edge coloring, then what you will have to do is, G will have a vertex V0, and that vertex V0 will have degree at least 4. Okay, if it have degree 2 means then easily you can do two-edge coloring. You are writing otherwise, right? If you are not able to do proper two-edge coloring, then there is a vertex V0 and that vertex will have degree at least 4. At least 4. Minimum it should have 4. Maximum you can have as much as you can, but minimum you should have 4. You should not have 3. Why? If it is 3 means it may form odd cycle, right? That kind of problems may arise. So the condition is there is a vertex V0, that V0 should have degree at least 4. Is that clear? Now let here already you are saying it's a case 1, right? Case 1 is our graph G is Eulerian. So here there is an Euler tour. That is what you are writing, an Euler tour, V0, E1, V1. From V0, start from V0 and ending with V0, right? It's a tour and it's an Euler tour. You are taking an Euler tour. Now you are dividing the edges of the graph. Okay, so here if there is a graph means graph will have e1, e2, e3, e4, e5, e6, that edges, e epsilon edges you will have. So you are dividing it into two sets. The edges, that is odd number of edges, e1, e3, e5, e7 are the odd edges. You are keeping odd edges in the set e1 and you are having even edges in the set e2. And what you are doing is you are coloring odd edges with the color I and even edges with the color what? Even edges with the color 2. That is what you are writing. Now after dividing it dividing the edges into two sets, what you are doing is you are coloring the edges. How you are coloring? The edges of the graph can be colored with two colors. What are the colors? 1 and 2, such that the edges of E1 received the color 1. Okay, and the edges in E2 is receiving the color 2. Is that clear? How many color you are using after dividing it into two sets? What you are doing? You are coloring one set with the color 1 and another one with the color 2. So you are doing two edge coloring. So that is why thus this E1, E2 is a two edge coloring, right, of G. So the color 1 and 2 are represented at each vertex of G. From this what? If there is a two edge coloring means what? If there is a vertex and from the vertex you are having two edges, each vertex are receiving what? Two colors. One is, this is 1, if this is 2 means, if this edge is receiving the color 1 and this edge is receiving the color 2 means, so what does it mean? This vertex, each vertex 1 and 2 are represented at each vertex. If for this vertex you are having two colors, right, at its two end, right, that is what you are writing. So the color 1 and 2 are represented at each vertex of the graph G. Two colors you are representing for each vertex of G. That is what you are writing. That is, if you are not able to do proper two edge coloring, then what you will do? The graph will have, there will be a graph. If you are not able to do edge coloring means, the graph will have a vertex V0 and that V0 will have degree at least 4. And what you will do? You will divide it into two sets, and after dividing it into two sets, you will do coloring. You will color one set with the color 1 and another set with the color 2. So that now you can do two edge coloring. That is how you have to finish the case 1. Now let us pass on to case 2. Case 2 is not Eulerian. Not Eulerian means what? You know that not Eulerian means there is no Euler tour. There is no Euler tour means what? There is no Euler tour means what? There is no way to have a cycle. Okay. So if there is a no cycle means G might have vertices will have odd degrees. If G having even degrees means what? Look at this. If G is having even degrees, right? 1, 2, 3, 4. Only if G is having even degree, then what? They form a cycle. Sorry, this is wrong. Look at this figure. What you are writing? Then G has a vertex of odd degree. Look at this vertex. 1. What is the degree of this vertex? 2. Even degree, right? So Eulerian means it will have the vertex. Each vertex will have even degree. Is that clear? You are taking G is not Eulerian, right? So the graph is not going to have the vertices of even degree. Each vertex of G will be what? Odd degree, because G is not Eulerian. Is that clear? So if that's so, what you are doing is you are considering another one new graph, that is G star. Okay, by adding a new vertex V0 in that new graph G star, what you are going to do is you are adding a new vertex, that is V0. That is, you are forming a new graph G star. How you are forming the graph G star? By adding a new vertex V0 in the graph G. After adding a new vertex V0 to the graph G, you will get a new graph, and that graph is denoted as G star. And in this G star, what you are doing? You are joining V0 with each vertex of odd degree. In our G, you are having each vertex of odd degree, right? So you are adding this V0 with the vertices of odd degrees. So when you add one vertex, okay, when you join one vertex, the odd degree vertex will become even degree. That is what you are saying. So you made it even. Now what you are saying is clearly G star is, because you made it even, right? Even degree. So you are saying clearly G star is Eulerian. Eulerian means there is an Euler tool. So you are writing like this. Now set you are having two sets, E1 and E2. You are splitting into two sets, the same way that you have done in the case 1. Now E1 intersection E and E2 intersection E form a partition of the edge set E of the given graph. You are partitioning the given graph. That is, this resembles this E1 comma E2. You are writing the same thing but in a different manner. Okay, look at this. If this is the graph, this is our graph, this is the edge set of this graph, and this is E1. That is, odd edges are like this. This is even edges. When I find E1 intersection E, what I will get? This, right? E1 is my E1 intersection E. E2 is my E2 intersection E, right? So the same thing, but they are written it in a different manner. So after splitting it into two sets, what you are doing? You are doing two edge coloring. You can do it. These are odd edges. These are even edges. So you can do two edge coloring. So now in this case too also you are saying each vertices can be represented with how many colors? 2 colors. What is the condition? The vertex should have at least how much degree? 2 degree. Okay. Hence the proof.